All right, well, given it's coming up to 5 minutes after, I think I am going to begin. So thanks everybody for coming. We at Insight Analytical try to host these webinars every month. Most of you are likely on our webinar email list, and so get regular emails to say when they're going on. You can always check on the Insight Analytical webpage. We have a whole section there for training where we talk about webinars and some of the training courses we're doing. So with that, I'm going to begin. And we're going to talk about the applications of near-infrared spectroscopy to hydrocarbon analysis, and specifically talk about some of the applications in gas plants, so natural gas processing. From a technology perspective, this webinar is going to focus largely on infrared spectrometers from JP3 measurements. It's a rather unique spectrometer, and so I do like talking a little bit about how it works and what we can do with it and why we see some really great applications for it. I'm going to start off talking a little bit about Insight and who we are. Although we are a manufacturer's distributor, so we're a buyer and reseller of products, we like to see ourselves as being somewhat different from your average distributor. We are a very technically focused company. My background came from the R&D side. Most of my company is engineers, engineering technologists, scientists, and we have a real kind of more of a techie focus than a sales focus. So we like to get actively involved in a lot of things that we refer to as part of our thought leadership programs. We do a lot of customer training through webinars. We're doing a full sample system course. We expect it's going to take about 8 months of doing a session every 2 weeks to cover a bunch of things you need to design or consider when you're doing the design or analyzer sample system. We're doing that course online and for free. So you can register for that again on our website under the training section of our website. We tend to carry very few product lines. We like to be experts in what we do and really understand how the technology works and how to apply it. And we also like to really work on applying it in applications where we understand our customers' processes and needs. So it enables us to try to ensure that we're putting the right technology into the right applications. As I mentioned, my background's from R&D, so we have a strong research focus. We develop a lot of our own products as well, especially for sample system components. And we'll be doing a webinar later this year in December about some of the Insight products and how they can be applied in analyzer sample systems. We very much are a spectroscopy focused company. My technical background is in physics as a spectroscopist by trade. And so we like to, again, work on products that we really understand how they work. And we recognize that a lot of the issues related in analyzer installations are sample system based. So we work a lot on the design and optimization of analyzer sample systems and components for those. When we're working with customers, we like to go through a very consultative sales process. So we usually like to have a customer who comes along, has a facility, and he has, an idea. So, geez, there's a measurement I really would like to be able to do. We like to interact with that customer, talk them through it, and innovate about what possible solutions there may be, and present those solutions for them. If we have agreement on a solution that they think might be a viable one for their application, we'll go off as necessary and invent or develop new pieces of technology that will help them integrate into a system, implement at their facility, and hopefully that customer will end up with a new process capability or process measurement capability. And so we like to sort of really focus that process may be a long one that requires a number of steps along the way. But what it allows us to do is really get deep into the application and how we're going to implement technology at a facility. So today we're here to talk really about JP3's near-infrared spectroscopy and how we can implement that as part of a real-time process control system. So we're going to look at that as ways to say, well, how do we put that technology in to get that extra dollar, that extra value out of an operating facility? So whether it's a condensate stabilizer, a fractionation plant, deethanizers, depropes, debutanizers, whether it's inlet gas analysis, what we want to talk about is How can we take technology, make better measurements there? Again, you got to realize our tagline is about making measurements matter. How do we make measurements there that are going to enable us to improve operations at a facility, hopefully increase production volumes, and add extra revenue to that facility? So one of the big advantages of the JP3 technology is it allows us to do chemical composition much like a gas chromatograph would, while at the same time being able to do physical properties like vapor pressure, viscosity, density, cloud point, flash point. We can do all of this based on the infrared spectrum. We can do it much faster than conventional technologies. We are typically 15 to 30-second updates. And that speed of response can often help us tighten up control loops. We also have no moving parts, very reliable technology, almost no field maintenance. And so as a result, we can have very high uptimes. So why do we like to use the near infrared as a means to measure hydrocarbons? Well, at first blush, one of the things we have to discuss or understand is what the spectroscopy of hydrocarbons looks like. And when I first launched or brought this technology to Canada, JP3 is a US company. I'm actually was just down there. I'm in Austin, Texas right now, where JP3's head office is. When I first brought this technology to Canada and started to talk to people saying, we can do measurements in your condensate and crude oil by shooting a beam of light through it, the first thing they would say is, have you ever seen my crude oil? It's jet black. Canada produces a lot of diluted bitumens, heavy oils. And the reason it's black is because the hydrocarbon fluids absorb all the visible light. And so as a result, if I hold up a sample of this hydrocarbon fluid, no visible light gets through it, and it looks black to me. But if we go beyond the red part of the spectrum and into what we refer to as the near infrared, the amount of visible light or amount of light that gets absorbed drops off. As we go to longer and longer wavelengths, less and less light is getting absorbed until we get out to about 1600 nanometers. And once we get out there, all the hydrocarbons start to absorb again. And the beauty of it is these hydrocarbons absorb with unique patterns, each different hydrocarbon having a differently shaped absorbance profile. And so we can qualitatively determine which hydrocarbons are present from the shape of the spectrum. By measuring how much light they absorb, we can also get quantitative information. So we can both qualitatively determine what hydrocarbons are there and quantitatively determine how much of them are there. At the same time, there's many physical properties, things like vapor pressure and viscosity, that can be correlated to the infrared spectrum. So by measuring the infrared spectrum, not only can I measure and determine individual chemicals, but I can also make an assessment of what the physical property of the entire matrix is. That crude oil has a vapor pressure of 90 kPa, and I can estimate that based on, or infer that based on the infrared spectrum. So what do we see when we look at different hydrocarbons in the near infrared? Top spectrum here is a natural gas liquid, which is a blend of a bunch of different components. The bottom one here is what pure propane would look like. So we can obviously tell the difference between pure propane and this blend of HCls. The top one just changed to normal butane. The bottom one is about to change to isobutane. And we can see again, there's differences in the spectrum of N-butane and isobutane from propane and from light hydrocarbons like NGLs. The bottom one now just changed to a mixture of heavier hydrocarbons, things like a stabilized condensate. And so the point of this slide is to let you see that the individual hydrocarbons in the pure state look sufficiently different enough that if we were just to look at the spectra of these individual components, we could easily tell the difference between them. Where it gets complicated, though, is when we have a complex mixture. A lot of the spectral features will tend to overlap. And so to the naked eye, it's difficult for us to determine exactly what the composition is just by looking at the spectrum. However, there's software we can use. We're going to talk about that in a couple of slides to separate out all these spectral overlaps. So near-infrared spectroscopy has been around for a long time. It's been being used in a lot of applications. There's a lot of NIR spectrometers in refineries doing things like vapor pressure of gasoline or olefin contents of gasolines, octane number or cetane numbers of diesel, octane numbers of gasolines. A lot of these applications have been developed, but they were developed around spectrometers that have moving parts and that required a fair amount of maintenance. And so refineries could easily do it because they have a lot of technicians, analyzer mechanics at a refinery to maintain this equipment. JP3 was launched to try to bring that same technology to remote measurements at wellheads, at crude oil blending sites where there's no analyzer technicians. So it required a number of advantages in order to be able to be put into applications like that. And one of them was better spectroscopy. Yes, Alejandro.
Hey Phil, how's it going?
I'm good, man. How are you?
Good. Thank you so much for these talks. Honestly, I've been finding them super helpful and just a great learning experience for all of us who are in the industry. One of the questions I had, Phil, in your previous slides. So when you mentioned that when overlap occurs between hydrocarbon absorption and the NIR spectrum, software exists to kind of elucidate each hydrocarbon's specific absorption. Is this kind of the same idea of when you're deconvoluting chromatographic peaks, like using a GC? Is this similar idea?
It's a similar idea, but it's easier on a GC.
Okay.
On a GC, you'll often get peaks that are separated in time. And
Mhm.
usually, if we've done a good job of developing a GC application, we won't be in a situation where, let's say, if this was the N-butane peak, we'll try to not be in a situation where something like the I-butane peak was eluting at the same time. So we try to keep the peaks from lining up on top of each other. We can do that by changing how long the chromatogram takes. In spectroscopy, we're limited, if you like, by the fundamental properties of the chemical. It turns out that isobutane and N-butane absorb at some of the same wavelengths. So there are always going to be some overlap. And so we have to use mathematical algorithms to deal with the overlap. Usually on a
Awesome.
chromatograph, we've separated the peaks in time.
So a question I also have just to follow up on when you were talking about viscosity and physical properties of an actual sample, is that information taken away from basically the quantification and the speciation of all of the components in your mixture from the NIR? Or is it that the actual spectrum gives you a value that's representative of the viscosity of the sample? Is my question making sense?
Yes, and it's a great question. I appreciate it. We don't, if we were going to try to measure all the individual chemicals and then calculate the vapor pressure or calculate the viscosity, we'd have to use some kind of equation of state. And often we don't, there's a lot of error when you do that. So we actually build a mathematical model that says, when we see a spectrum like this, we take a sample, we send it to the lab, we get them to measure the viscosity, and we build a model that goes directly from spectrum to viscosity without having to go through the intermediate part of trying to say, well, which chemical species are there? So if we sell, for example, a vapor pressure application, we don't try to measure which chemicals are there. We just say, we can tell you what the vapor pressure is.
Awesome. Thank you so much, Phil.
Yep, my pleasure. Thank you. So a few things that JP3 did or has done, which separates their technology from the technology that's traditionally been used in places like refineries. One of the things they do is they use a very unique spectrometer. And so they took a lot of the advances that had been made in telecommunications with these laser diode spectrometers. And those laser diodes had some really great properties that were a requirement of telecommunications. Long mean time to be between failure, extremely reliable. They're lasers, so extremely narrow bands, monochromatic light. And they took all of those advantages, but they made it be broadly tunable. I'll explain what I mean by that in a minute. So normally a telecommunication laser will fire at one wavelength and one wavelength only. If people are doing things like tunable TDLAS or tunable diode laser absorption spectroscopy, they'll use temperature and current to move that wavelength a little bit, usually by less than about 1 nanometer. The JP3 technology has built a small spectrometer that can be put onto a silicon wafer that can tune across about 450 nanometers. So it goes from 1350 nanometers all the way out to 1800 nanometers. And that means it can look for many different chemicals, all in the same analytical piece of laser hardware. It's extremely repeatable as well. And so, which is important because it lets us do calibration transfer, and it can do that scan from those wavelengths at very high resolution. So in small steps, it'll typically go 1350 to 1350.5 nanometers. So it'll typically work in half nanometer steps. JP3 has a newer version of the spectrometer that's coming out for some applications that'll do that in 30 picometer or 0.03 nanometer steps. So even higher resolution. The other thing is it's a no moving part spectrometer. So there's really no field maintenance that can be done on the spectrometer. The light source lasts virtually forever, 10 years or so. And there's no moving parts. The spectrometer is very robust. The other thing that needed to be done is to do that mathematical algorithm that takes and separates out the overlap of the spectra. And there's been a lot of advances that have occurred in technology that we've implemented in the JP3 spectrometer. So one is, of course, that computers have gotten faster. Everybody's talking about AI now. So we have things like pattern recognition algorithms. Even our phone does it, right? It determines, it looks an image of our face and says, oh yeah, that's Phil. Or a fingerprint, or can recognize voices and convert the waveform associated with our voice into actionable data, text. Well, we've taken all of those algorithms, which when they're used in these sorts of things are referred to as chemometrics. Chemometrics is the art or science of applying pattern analysis to chemical data. So we can take that spectral data that we measure, that infrared spectrum, we take the spectroscopy, we add in chemometrics, and from that, we push out information like concentrations of chemicals, physical properties, etc. So this ability to do better numerical analysis, and then one of the other things is that when they were doing spectroscopy at, say, refineries, big users, petrochemical companies, the Shells and the Exxons of the world, would say, well, we can do all the chemometrics. We have scientists in our company that do that. The JP3 technology has been built to have cellular connections to remote devices, and we can do all of the chemometrics based on customer data and provide the mathematical modeling. So it means that a small company that just wants to put a butane blending skid out in the middle of nowhere doesn't have to have some scientist on board to build the mathematical models. Another important piece of this is to do the sample systems better, or to make the sample systems less complicated. So when we think about traditional analyzers like online chromatographs or online vapor pressure analyzers, we often associate with them a complicated sample system where we do a lot of filtration and pressure and flow control. The JP3 installations are extremely simple. We have what we refer to as a flow cell. It is a block of 316 stainless steel that is rated to 1500 PSI. So we can put this directly in line in an operating process that's up to a 600 ANSI class system. Inside that stainless steel block, there are two synthetic sapphire rods. We use synthetic sapphire because it is the second hardest thing next to diamonds. So it doesn't get scratched by sand, clay, bitumens. It doesn't get attacked by chemicals like H2S. It's extremely robust. We allow process fluid to flow between the two sapphire rods. We bring the laser light in over a fiber optic and shoot it across the flowing fluid. This allows us to let that beam of light now interact with the fluid. We're able to install that with no sample conditioning to speak of. We look for some source of differential pressure that drives flow from the high pressure side over to the low pressure side. So this might be an orifice plate, a control valve, process pump, We get flow continuously going through the flow cell. We put that flow cell as close to the process as we can. By putting it close to the process, we ensure that we have very little transport lag. Basically, we get sample into that flow cell almost immediately after it leaves the process. We return all of that sample directly back to the flowing process. So this can give us really fast response. So then an installation becomes very simple and robust. We mount that flow cell out near the process. We drive process fluid through it. We mount the part that has the spectrometer, the brains of the system, someplace else. Control room, MCC building. We're not going to bring any process fluid back to this. This is really what separates this from traditional analyzer installations. In a traditional analyzer installation, we'll bring process fluid from the process over to where the analyzer is, often inside some kind of an analyzer building. And we bring that fluid into the building. So now we have to worry about gas detection. We have combustible fluids. We have potentially sour fluids that have H2S in them. And so now we have to worry about, do I have protection against leaks? Am I going to potentially create a hazardous environment around the analyzer? Here, the analyzer is someplace else, MCC building. We shoot a beam of light over fiber optics. We bring that beam of light back, measure what happened to the beam of light, and from that, we determine things like the chemical composition and or the physical properties. And in fact, we can have one of these devices shooting fiber optics out and bringing it back from different places in the plant. So this one might be on a condensate stabilizer. We're measuring liquid condensate vapor pressure and butane content. And we might have another cell that's measuring in the gas phase on an overhead, inlet separator overheads. Completely different measurements in different places in the facility being done with the same technology. So typically we can handle up to 4 sample points. There is a version that can go up to 8 as well, or there's 1. So there's a few different versions of the analyzer. We've been doing this for quite a while now. We pull lab samples in a lot of plants. We have the largest consolidated database of near-infrared spectra for many different products. So this graphic is supposed to show that the different types of products cluster in different parts of what we refer to as our analytical space or principal component space. And so the different colors on the graph represent different chemical species. So for example, if I look over here, I've got a whole bunch of dark green diamonds, and those are natural gas liquids. Natural light liquids tend to show up on this side of the spectrum or of the component space. Heavier liquids like these light blue ones, these light blue inverted triangles are crude oils. And so we have this entire library now of different types of samples from different types of process. Alejandro, yeah, there is a limitation on, so the question in the chat was, is there a limitation to the fiber optic link's ability to transport the light? There isn't really, there is a limitation. It's not the biggest limitation. The biggest limitation is it's a very customized fiber and it can get expensive if we go really long. So our longest installation right now is about 1,000 feet, 300 plus meters. We like to keep it shorter than that just because the fiber runs get to become expensive then. And if it gets broken in the field, it becomes an expensive maintenance item. So here's a typical Canadian installation, if you like. You can tell it's Canada because you can see the snow. So we're out at a condensate stabilizer. We've mounted this 1 meter by 1 meter fiberglass box out there. Inside that fiberglass box, there's a heater. There's the JP3 infrared cell. You can see the fibers. Actually, I'm going to zoom on these. So there's the installation out near the condensate stabilizer. If we look inside the box, we see that there's that JP3 flow cell in the middle. It's got the little gray heating insulating jacket over it, 2 white boxes that protect where the fibers couple. There's also temperature, pressure, flow measurements in there. So we put that 1 meter by 1 meter box out there. On the left of it, you can see a couple of insulated and heat trace lines coming into the box. So there it is again out at the facility. Back in an MCC building, the JP3 spectrometer unit is just mounted on the wall in this electrical control building. And when we open the JP3 unit up, the black box at the bottom is the spectrometer. There's you see four silver dots on there, basically. Those are the 4 fiber optic connection points for the return lines. Above it, there's a single board computer. Above that, there's an Allen Bradley PLC. Above that is power supplies and our network communication hardware. So that's the complete installation, and that could be handling up to 4 different streams and measurement points in the facility. So if we look at something like a condensate stabilizer at a gas plant, we would like to optimize it. Typical layouts in a gas plant might be that we're bringing in feed from a number of different wells. It goes through an inlet separator that lets gas come off on the top of it. No, they're running sequentially. So the question was, are the measurement points from several different points running simultaneously? There's a beam splitter in the spectrometer that sends the laser out over 4 points, but it only measures the detector on 1 point after the next. So the 4 points get updated about every 15 seconds. So 15 seconds on one measurement, 15 seconds on the next, 15 seconds on the next, 15 seconds again, then back to the first one. So with 4 measurement points, you get an update of each measurement point about once every minute. Gases separated off the top of the inlet separator, water off the bottom, hydrocarbon fluids coming off of the middle, if you like, of the inlet separator. This might go to a coalescer where they'll knock out any entrained water and off to a condensate stabilizer. They are basically boiling off the light ends. So they have heat going at the bottom here. They're boiling off the light components like butane and propane to the overheads, keeping the liquid condensate at the bottom. The condensate is essentially a C5 plus stream. So they have to put energy in to reboil it. And then the vapors that come off the top, they have to put energy in to recompress it. And we want to produce our product over here. So the goal of condensate stabilizer optimization is to only boil out as much as you have to. So if we overboil it, we'll push more butane to the top end, and we're allowed to have some butane in our condensate. So if we overboil it, we'll produce less volume. We'll use more energy on the compression side. We'll use more energy on the reboiler side, and that'll lead to higher environmental emissions. So by optimizing it, we can increase our product volume, lower our energy for compression, lower our energy for reboiling, and lower our environmental emissions. So all of these add some economic value to the facility. So to optimize the stabilizer, it requires that we measure chemical composition. Chromatographs are great analyzers. They work really well, provided we can give them a good sample they can work with. Online chromatographs have really struggled in condensate stabilizer applications. Because we're looking at the fluid that is coming off the bottoms of the tower, it tends to have a lot of things like sand, clay, and dirt in it. And this can be very difficult for an analyzer sample system. Also, when we look in northern Canada, the condensates are very waxy. And so if we get any cool spots in the sample system, it will tend to wax off and plug off. Things like chromatographs, online vapor pressure analyzers tend to have small tubing, 1/8-inch tubing. They have tiny injection valves. And so what we tend to run into a lot of times is when the analyzer is working, it measures really well. But if we have sample system related issues, it can lead to high maintenance, high operating costs. We worked with a facility that had tried to, for 2 years, to get their online chromatograph to run reliably, and finally just said, we're just going to replace it with another technology. And so we put a JP3 in there. GCs on liquids analysis can be complicated. We'll often have to have ways of vaporizing the sample. There's often complex sample systems, small tubings, and it can just be difficult to get them to run. And we really want to do, in Canada at least, it's a little bit different than the US and other parts of the world. In Canada, we have to do an analysis of how many light ends, C1 to C4 hydrocarbons there is in the condensate. We have a thing called the deemed C4. And so on a C5 plus or condensate specifications, we have penalties if the density is too high. We have penalties if the sulfur is too high. But on both of those penalties, we also get paid a bonus if we're below specification. So if our density is low, we actually get a bonus for our condensate. If our density is too high, we pay a penalty. On DMC4, it's different. On the butane and less composition, we have to be less than 5 liquid volume percent. We pay penalties if we're over on that. So if we have 6% butane in our condi, we only get paid. They basically say it's as if you produced 1% less. You gave me 100 barrels, but I'm only going to pay you for 99 because 1% of it was too much butane. But if we're under our DMC4, we don't get any bonus. So if we're under our DMC4, we didn't produce as much volume as we could. So we basically get penalized if we've got too much, and we get penalized if we've got too little. It'd be like if they controlled the speed in a highway and said, if you're doing 60 miles an hour or 100 kilometers an hour, you're fine. If you're below that, you're going to pay a speeding ticket. And if you're above that, you're going to pay a speeding ticket. It would make it a lot more difficult and more important to you to precisely control at the right value.
Phil, I have a question.
Yep.
So based on your last slide with the C4,
Yep.
so if you have less than 5% liquid, then that's a penalty for being over or under. That was a little unclear to me.
So if my stuff that was coming into my stabilizer had 10% butane and 90% C5 plus, and I'm allowed to have 5% butane over here, if I run my condensate stabilizer perfectly, I'll boil 5% of the butane to the overhead, and I'll have 5% butane when I get down here. If I boil it too much, I'll drive 6% butane to the top, and I'll only have 4% butane down here. And that'll mean I produced 1% less condensate. If my plant was capable of producing 100 meters cubed per day at 5% butane, I'll only produce 99 meters cubed at 4% butane. So the pipeline company won't make me pay a penalty, but I didn't produce all of the condensate I could. I produced less volume. In refineries, they do this based on vapor pressure, and they call it RVP giveaway. If they don't hit as high a vapor pressure, blend as much butane in as they can to hit as high a vapor pressure as they could. It's a barrel of butane that didn't get sold as condensate, and it went over to their natural gas side where they don't get paid very much money for it.
So basically the goal here is to essentially be at like 4.99%
Exactly.
butane on your condensates.
Yeah.
Okay.
So 1 meter cubed of condensate is worth about $600 Canadian, and 1 meter cubed of LPG might be worth $150 Canadian. So if the butane goes over to their LPG side, they're getting paid $150 for it instead of getting paid $600 for it.
Okay. That makes a lot of sense. Thank you for clarifying that.
Yep. So condensate analysis for the JP3 is old application in Canada. Basically, all of the condensate that goes to Fort Saskatchewan, which is kind of the central hub for condensate, goes through a JP3 analyzer. And with the JP3, we can do real-time analysis of the DMC4, the butane content. We can do real-time analysis of the vapor pressure, the viscosity, and the density, all off of that infrared measurement. So one analyzer giving you chemical composition, vapor pressure, viscosity, density. So as I mentioned, so this is a typical installation up in Northern Canada. In the US, because the climate's not so bad, not so cold, they actually just install the analyzer outside. So this is an installation in the US. They have the JP3, this is a single stream analyzer sitting out near the facility. This is the infrared flow cell that it's connected to. So this is the analyzer, flow cell. They have a sample point over here and a sample return over here. They're just sampling across 2 entries on the process line. And that's a complete installation. Some people want to go you want a big metering building where they're pushing a lot of product through, a big custody transfer building. They'll put in additional capabilities. So this was a system that we put together for one of our clients. The JP3 flow cell is sitting over here. They wanted to automatically be able to pull a grab sample when necessary. So we have the PLC, item number 3 there is controlling that spot sampling. We also have a solvent flush tank sitting over here. They were concerned the condensate could be very waxy, and they wanted the ability to automatically backflush the system with toluene to wash off any condensate or waxes. So we have a solvent flush system. And while they're doing real-time analysis, they're also pulling in composite samples where they take a sample of the fluid and average it over a period of time, like a week or a month, to get what the average composition is. So the question becomes, well, how do we do on the measurements? So here's condensate composition. And you will get a copy of all these slides, by the way, after this presentation is done. So this slide's a little bit complicated. On the x-axis is the laboratory measurements of propane and isobutane. On this y-axis is the JP3 measurements of propane and isobutane. So propane are the blue dots. You can see all the blue dots are sort of down in this region down here. There shouldn't be very much propane in your, usually they have upsets where they get up to about 0.5%. The isobutane are the red dots. Oh, and again, so what we see is that there's a 1-to-1 correlation between the infrared measurements and the lab measurements. Slope is very near 1, y is 0.98x, so we have a little bit of bias in there perhaps. And there's a bit of scatter because there's error in the lab measurements and error in our online measurements. The red dots go all the way up to about 1.3%. Those are the isobutane. And they go as low as, it looks like there's one down here, is 0.1%. So again, we've covered a fairly wide range of isobutane depending on their operating conditions, and been able to do the analysis with the infrared device in about 0.2 LV% or better. Up here is the normal butane on the lab measurements, and on this side is normal butane from the infrared. And I have to put them on different axes just because of the range they're on. They go as low as about 1.5% all the way up to 5%, and the N-butane are the green dots. So again, excellent correlation, good agreement between the lab and the online analyzer. Now, the beauty of this is the system just runs continuously. They haven't had any issues with it waxing off. If they do get wax in the sample line, they can just back flush it with a Baker pump of diesel and push that wax out, and the system goes right back up to running again. Virtually zero maintenance. So little maintenance. We had a client once tell us there isn't a display on the analyzer because he hadn't been out to see it for so long, and there was a display on it. The DMC4 specification in Canada requires we add these values, we multiply the propane by 3, add in the iso and normal butane. And so when we do that, we get again, we get this nice 1-to-1 correlation between the JP3 infrared measurements on this side, lab on the x-axis. And we agree to the lab within about 0.14 LV%. So it shows we can do real-time analysis of the DMC4 content in a natural gas condensate and agree with what the lab gets. That lab piece is important. We often validate analyzers by running a calibration standard, and that's great. But all it proves is that the analyzer reads correctly. It doesn't prove that the sample system is getting the right sample there and that we're actually reading what is in the process. The lab samples is what we base our custody transfer agreement on. If I'm going to pick something in the group. If I'm selling condensate to Kirk, we have an agreement that it has to be less than 5% condensate, and we have or butane, and we agree that the way we're going to determine that is based on the lab. And so if we can use the JP3 to predict what lab results would be, it means it predicts whether I'm meeting my custody transfer requirements. That custody transfer agreement may also include vapor pressure. And so on the same condensates, they tend to control tight APA. And so you can see most of the data is clustered out there. Occasionally they got some high ones here. There's an ASTM reference method for vapor pressure, ASTM D6377, and it has a repeatability specification of plus or minus 2.48 kPa. You can see that we agreed to the lab to within better than the ASTM method's repeatability specification. We agreed with the lab with about plus or minus 1.75 kPa. I'm doing another webinar in a month from now. We're going to talk about crude oil applications. So we're going to talk about doing vapor pressures in crude oils as well. We can be using the same analyzer to do deethanizer bottoms. So usually on a deeth, the important thing is the ethane and the propane. There's a specification on the ethane to propane ratio. So we want to be able to measure ethane and propane and make sure we're on spec for our ethane propane ratios. So again, this is a range of data that was acquired over a significant time. This is over 5 years, a range of operating conditions, different pressures and temperatures. And we have a reasonably wide range of propane content over here, again, with a 1-to-1 correlation between the lab and the JP3 and the ethane concentration, lab to JP3. So this allows them to do real-time measurements of the ethane, the propane, calculate the ethane to propane ratio, and use that for controlling the deethanizer towers. In the US, they'll often put in a heater treater on something like crude oils or condensates because they have high volatiles in there and they want to boil those out. So again, this was a facility, their specification was they had to be less than 9.5 PSI. The JP3 in control, they're trying to control with an online analyzer, but it wasn't another online vapor pressure analyzer had issues with reliability on it. And so the way they did their control was they just said, we're going to turn the heater treater on fairly hard, boil a lot of the stuff out. That got them to low vapor pressure, turn the heat to the heater treater off, let it rise up for a while, and then we'll turn the heat back on again. And so they would oscillate. And they didn't want to go over spec, so they left a fairly wide margin between what they controlled at and what they were allowed to put out. This led to less production volume. When they put the analyzer in, they said, we're going to try to control to be below about 9.25 pounds. And they run right around there between 9 and 9.25. Got a lot better control on their vapor pressures, real-time control, and this allowed them to increase their production volumes. It may not seem like a lot, but 1 or 2% increase in production can be a lot. If I'm putting out 500 cubic meters a day or 3,000 barrels a day, which isn't a lot of production, I mean, it's a pretty decent sized stabilizer, and I get paid $600 a cubic meter, well, 600 times 500 is $300,000 a day. If I can increase production by 2% by running tighter to specification, 2% of that is $6,000 a day. My analyzer installation was $200,000. I pay that off. So small improvements on these operating vessels can print a lot of money. Sorry, I'm coming up to time here and I am just about done. When I launched JP3 in Canada, there were 0 installed base. JP3 only came on the market in the US around 2014. We brought them up to Canada starting 2016. We have about 60 JP3s up and running in Canada right now, about 100 measurement points. So all the Canadian ones, most of them are up here, a couple Saskatchewan, Southern Ontario, someplace. I think it's down here. There's about 400 JP3s installed across North America. There's about 80 customers using them worldwide, getting close to 1,000 measurement points now. We're on every major basin for oil and gas production. We do a good mix of crude oil samples, condensates, NGLs, refined products, and natural gas. So a summary and conclusions, this infrared technology has allowed the method to be applied across a wide range of products and applications. We do everything from natural gas liquids to gasoline and diesel to crude oil. It provides robust real-time analysis of crude oil and other hydrocarbon fluids for a range of physical properties and put them in, say, we just want to measure vapor pressure. And then a year later, they'll say, we'd like to add viscosity in. We don't change any hardware, we just change software. These devices have been designed to be field robust, and they're proven now in process applications with very minimal maintenance. For your time, I will mention, we talked about the JP3 technology, but Insight Analytical carries a wide range of other technologies, and we'll be doing webinars on all of these technologies over the next period of time. We're going to talk about JP3 again next week, but I'll also talk about Rigaku next week because we're going to talk about measurements in crude oil and crude oil optimization. We do products like mass spectrometers, online Wobbe index and burner control analyzers, total sulfur analyzers, water quality, trace analyzers in purity gases, and a number of other applications. You'll get a copy of all the slides. I realize I should have put my email address on the front. I left you some email addresses of people to contact if you want to get more information. And please do reach out to us if you have a hydrocarbon processing application. That wraps me up. 1 minute before my due time. So if there's any questions, I'd be happy to address them. A few people dropping off. So if there aren't any questions, I'll wrap this up fairly quickly. But again, thank you all for coming. We will be doing another webinar in a month right now. I am doing some online sample system courses. So if you're interested in analyzer sample system design, I'm doing it at 3 different times, one for Asia Pacific, one sort of around European time, and one on North America time. So the next ones are coming up are Europe and North America next Thursday. So again, check out our website. Easy to register there. Thanks everybody for coming. Appreciate your time.